Today we are looking at the rules for the Fourier transform and at the convolution theorem, which together let us solve partial differential equations. First, the rule for a first derivative. The Fourier transform of the first derivative of a function equals e times omega times the Fourier transform of the original function. In other words, taking one derivative in the ordinary domain corresponds to multiplying the transform by I omega in the frequency domain. Next, the rule for a second derivative. The Fourier transform of the second derivative of a function equals negative omega squared times the Fourier transform of the original function. So taking two derivatives corresponds to multiplying the transform by negative omega squared. Now, the convolution theorem. This theorem states that the product of two Fourier transforms in the frequency domain corresponds to the convolution of the two original functions in the ordinary domain. So multiplying transforms together is the same as convolving the original functions. These rules turn solving a partial differential equation into three clear steps. We transform the equation itself, and we transform the initial condition using the derivative rules we just stated. Step 1 is to transform the equation and the initial condition. Every derivative in x becomes a multiplication by I omega or by negative omega squared in the transformed variable. Step 2 is to solve the resulting ordinary differential equation. Because the partial differential equation has now become an ordinary differential equation in the transformed variable, it is much easier to solve directly. Step 3 is to invert the transform to recover the final solution in the original variable. Often this inversion is done by recognizing the solution as a product of two transforms and then applying the convolution theorem to write it as a convolution. To check this, let us confirm the second derivative rule directly. Differentiate the Fourier transform integral twice under the integral sign with respect to x. Each derivative brings down a factor of I omega from the exponential term, so two derivatives bring down I omega times I omega, which equals negative omega squared. This confirms that the transform of the second derivative is indeed negative omega squared times the original transform.